To a pollution prevention webinar series hosted by the EPA and the Center of Sustainable Energy and Environmental Engineering at ECU. Today's webinar is about energy efficiency opportunity in industrial facilities, data monitoring, and insights. My name is Carol Masarra. I am an assistant professor at the Department of Construction Management and also the director of the coastal resilience at the Center of Sustainable Energy and Environmental Engineering. Next slide, please. So the center mission is student success, public service, and regional transformation. Next slide, please. So what we do at the center, part of our work at the center is on-site energy, pollution prevention program, lean assessment. We do regional and on-site P2 energy training, regional workshops, technical and engineering support, cash flow and market analysis, return on investment. Next slide, please. So some of the webinar housekeeping that this webinar will be recorded. The speaker presentation will be available. If you can save your question to the end of the webinar, that would be great. If you want to donate to the center, please use the link on the screen. Also make sure that your microphone is muted. Next slide, please. So our speaker today is Dr. Lian Zhang. He is an associate professor at the University of Connecticut. He received his BE and ME degrees from the Center of Intelligent and Networked System, Department of Automation from China in 2002 and 2004 respectively, and his PhD in engineering in electrical engineering system from the University of Michigan in 2009. He was with the Department of Industrial and Manufacturing Engineering, University of Wisconsin from 2009 to 2013. He is currently an associate professor with the Department of Electrical and Computer Engineering, University of Connecticut, and the director of the Yukon Industrial Assessment Center. His research interests include modeling, analysis, improvement, design, control, and smart operation of manufacturing systems. He is also the co-founder of Smart Production System LLC. Welcome, Dr. Zhang, and you can start your presentation now.
Thank you very much, Dr. Masara. I hope everyone can hear me clearly. My name is Lian Zhang again. I'm the director of the Yukon Industrial Assessment Center. And in today's webinar, I want to talk about some of our findings through our IAC operations and share some of the insights we obtained, and hopefully can help audience from both academia organizations or industrial professionals to help their future operations. So here's the outline of this talk. First, we'll just explain who we are as an IAC and what we do. We have two basic approaches. I want to dive in a little bit after that. One is the low-hanging fruits approach, and the other is the data-driven approach. Both of them will go in parallel, side by side with each. And then I'll discuss some of the resources and some of the new IAC programs that hopefully can bring more benefits to the general audience of the IAC program. So the Industrial Assessment Center program is under the Department of Energy. It has been in existence for over 40 years. The program website is iac.university, where you can find a whole lot of information about the IAC, especially we'll see there are over 30 IACs around the nation, all of them hosted by a higher education institution to cover different graphical areas. And through the 40 plus years of history, the IAC program has conducted over 20,000 on-site energy assessments for small, medium-sized manufacturing facilities in the nation, with over 150,000 recommendations in terms of energy efficiency measures. In this year alone, 2023 up to today, there have been 523 assessments conducted and recorded in a public database maintained under the same website under database, where the general public can view the results and learn about the outcome of the IECs. And we're going to revisit the 500 numbers later on in this talk. So this is the geographical distribution of the IECs. It covers different regions, as I mentioned, across the entire nation, from the West Coast to the East Coast. Our Yukon IEC was one of the youngest IECs in the cohort. Were established 2021, 2 years ago, and we started our assessment work last July 2022. And so far, we have conducted 23 on-site assessments. 20 of them have been recorded into the database. And as part of the mission, we also provide trainings to engineer students in different disciplines. And over 15 students have been involved in our IEC program in various activities. So here are some of the pictures of our student team carrying out energy assessment in different facilities. We have a wide range of devices and instruments that we can bring on site to investigate, measure, and explore different opportunities that can bring energy efficiency benefits and opportunities to the manufacturing facility. And I would explain how we use these to collect data and how we can use the data to formulate energy efficiency measures for our industry clients. This is our geographic footprint. You will see a number of dots in this map. The green dots represent the assessment that have been completed by our center in the past year. There are a few blue ones. They represent the ones that we have established contacts and are in the pipeline to be scheduled on-site assessment in the near future. And as I mentioned earlier, we have done 23 assessments in the past year. These include two-day assessments of larger industrial facilities. 6 are being contacted, and we are receiving more in a couple of days in the recent days as well. Our geographic servicing area includes the state of Connecticut. This is where we start, kind of our home base. We also service Massachusetts, Rhode Island, in the downstate areas of New York. As you can see, we have done a few assessments in Long Island, New York, in the past year as well. The list of our recommendations can be found on the IEC database, iec.university database, which lists the principal product of all the assessment facility we've been to, and this will be true for all the other IEC assessments in the nation as well. What I want to highlight here is you'll see some of the rows are highlighted in orange or in yellow. These represent facilities that are in underrepresented or disadvantaged communities. As part of our mission, we want to bring benefits to those communities to ensure our practice in diversity, equity, inclusion, especially in terms of energy equity, which is part of our mission. So with that, I want to dive in a little bit and talk about our general approach. And when people talk about energy assessment, they could be viewed by some as a relatively advanced work done by a group of highly trained industry professionals or professionals in a university like the IECs. This is true, but there are also a lot of opportunities that can be done with little to none capital investments and will have almost immediate payback. So in the IEC system, there is a book that summarizes hundreds of standardized energy efficiency measures. They're coded into this numerical system. They're called ARC, Assessment Recommendation Code. So among those recommendations, 2.8121 represent this recommendation of applying for tax-free status for energy purchases. So this particular assessment recommendation was brought up 38 times by the IECs in the nation in 2023. As I mentioned, there are about 500 done in the so far in 2023. So this is about 15% of the assessments in the past year. So 1 in 6 assessment the IEC has been to are observed with opportunity in there. And the average annual saving is significant, $32,000. And I want to give an example from our perspective. We're in the state of Connecticut. The sales tax rate is 6.35%. And the state regulation says the gas and electricity used directly in fabrication, production, agriculture at no less than 75% of the level of those utilities used can be exempt from the sales tax or use tax of utilities. This 75% number could be changed, could vary across the nation. Different states have different levels. Some have 50%, some have similar 75%. But for most of the industrial facilities, if you are actually doing manufacturing certified manufacturing operations by the state or by utility providers, then they shouldn't be charged by the 6.35% sales tax. In Connecticut, we have another kind of tax credit called gross earning tax reduction rider, where manufacturers with this SIC code between 2003 and 999 can receive a bill credit equal to the product of 8.5%, the rate, times the delivery charge in their electricity bill. And this is the case for Eversource and the UI, which covers majority of the state. And if we do a simple math, right, assume the electricity charge, which has both supply and generation, and then deliver and transmission. Let's say 55% of electricity cost is for delivery, which will qualify for this 8.5 bill credit. And then the potential saving of such energy cost reduction measure in the state of Connecticut will be the 6.35% tax and half of the 8.5%. So that's overall 10% reduction in their electricity bill by simply certify with the state and with the utility providers that the facility is a qualified manufacturer. This is not the case, and this is not the case for majority of facilities I've been to, the ICs I've been servicing. But this represents kind of an icon showing that there are opportunities that are out there, very easy to get, and applying for those takes literally no cost and can have significant gain. And we have seen this opportunity not only to very small facilities that are spending like $100,000 on energy, but we have seen this in larger facilities that are spending $700,000 on energy per year. But as I have mentioned, some of you have seen in the flyer of the seminar, start internal and try to get the low-hanging fruit. Start with your electricity bills, your gas bills, and find if there are opportunities. So we talk about tax-free status. Under the same category, there is another one, 2.8114, says change rate schedule or other changes in utility service. So we know when we have electricity bills, especially for industrial facilities, depending on the size of the use, right? They have small use, intermediate use, and larger use, and they're charged by different rate structures. In this particular recommendation, many of them are related to that particular rate schedule change or supplier change, and this is recommended less, only 23% of the IC assessment in 2023. Significantly less, but they still represent about 5% of the assessment the IC have done, and usually this can generate also a large saving with minimum investment, little to none investment. And again, I want to give an example of what we have seen from our own eyes. This is a screenshot of a news article published last year in November. that the customers of two major energy suppliers of the state will see their electricity generation rates double. And here I have a detailed table to show the numbers. This is the Eversource business standard service generation supply rates in units of cents per kilowatt hours for the past 3 years. 2021, the first half of the month usually higher, about 8 to 10 cents per kilowatt hours, and then dropped in the second half. 2022, we have an elevated cost, much more than we have 2021, but still within the certain range. And all of a sudden, if we look at this particular column, from January 1st, 2023, the generation cost increases from 14, 11, 12, 13, 14 cents per kilowatt hours to 22, 23, or 25 cents per kilowatt hours. But this is the standard service generation supply rates. The customers have the flexibility and the freedom to choose have their electricity or energy supplied by other suppliers. However, what we have seen is some of the companies, for one reason or another, still use the standard service rate for the first half of 2023, which is about, we use this 23 cents per kilowatt hours. And I want to just do a quick demonstration. If a factory is using under 50,000 kilowatt of electricity in the first half of this year, enter the standard service rate of 23 cents, but have the potential to switch to another supplier at 12 cents per kilowatt hours, which is very common among the suppliers that the customer can search easily on the Energize CT website established by the Energy Efficiency Board of the state. A simple math says by switching supplier, which is a seamless procedure, painless, with almost no trouble in between, the saving can be 16,000. And similar to the tax exemption recommendation, these recommendations are very little cost to zero cost at the customer, but can render a large benefit in terms of the energy cost. They're still going to be using most likely the same amount of energy, but the actual cost, the dollar amount they're paying, can be significantly reduced. So as we see in the title, I want to talk about data monitoring. And this is something I want to stress also, that when we talk about data monitoring, it doesn't mean all those, pressure, temperature, volume, those are data, of course, but data could be, the usage, the charge structure, the charge rate, the policy changes, regulation changes. Those will also affect the basic data that can have a grand effect on the overall operating and operation of an industrial facility and other organizations as well. So let's step a little deeper into the engineering side of this, right? We talked about the previous two slides. I want to talk a little hand fruit. There are numbers, there are data, but they're more on the business side. Let's talk a little bit about engineering. So a lot of industrial facilities operate with a fleet of equipment with different sizes, functionalities, objectives, and also different power ratings. And one of the first things I would recommend everyone to do when we go to assessment is to understand the baseline of the energy usage. And the very first step is to have a rough idea of how much energy will go into each particular equipment, especially if it's one of the energy hogs on the floor. So there's another quick math, right? If you have 100 horsepower equipment that runs at 60% load on average, continuously 24/7 for the whole year, and let's assume 1 kilowatt hours of electricity costs 15 cents, which is quite typical in the state of Connecticut and also in a lot of the New England states as well. Right, so we do a simple conversion from horsepower to kilowatt, and then multiply this by the load factor, the number of operating hours, assuming it runs continuously, and multiply by the charge rate, 15 cents per kilowatt hours, and this will give us close to $60,000 of operating costs for the energy alone of this particular facility. And this is a lot of money just for energy. It's not about raw material, not about human resources, workforce. And if there's a chance to reduce the usage of this equipment by even 10%, that will be significant. So usually when the facility has a fleet of equipment that has this large power ratings, the question to ponder is, can we reduce the usage of the equipment? Or is this equipment running at all when it's not really needed? Some of these answers to these questions can be addressed sometimes easily without taking a lot of measurements or calculations. But if from our practice, usually when people get busy, when you have limited workforce on the floor, a team like the IEC can help. And what we do is we can deploy sensors and data loggers to help understand the operating profile of this major equipment and come up with the actual numbers of how much opportunities we can actually squeeze out of the operation of equipment like this. So first, we want to start with the process requirement and equipment nameplates and specs. Those things, again, do not really require some devices or instruments that a typical manufacturing plant do not possess. For instance, this is an engineering schematic of an Akuma Janos CNC machine. We're not going to all these details, right? I'm only going to focus on this part. Right? Let's talk about the air inlet. This is the requirement of the compressed air into this particular machine. It has a number of things to talk about. The required capacity, 500 liters per minute. We can convert it to how many cubic feet per minute. It's about 16, 17 cubic feet per minute. But also it tells what is the minimum pressure that the compressor will be needed to feed this particular equipment. Of course, it's in megapascal. We can convert it to PSI, and it's about 72.5 PSI. And we serve these machines, and this is very typical in Connecticut. We have a lot of job shop or machine center based manufacturing facility in the region. And they have air compressors serving this fleet of CNC machines on the floor. And this is the technical data of a Quincy 75 or 100 horsepower air compressor. It has the capability to set their air pressure to 125 psi. The question is, if we have a fleet of machines like this in the facility, which requires about 72.5, what will be the sweet point or sweet spot for the compressor to have the pressure set point configured? For many of the facility we've been to, the pressure set points were liberally set at over 100, sometimes 120, sometimes 115. Well, the actual process do not actually need that much. These type of most of the machines we've been to is on the floor usually use 80 to 90 psi's as their requirement. Even with a certain safety margin above that, setting it at 120 or 115 is not necessary. It's not necessary at all. What usually happens is there are regulators, governors installed at each particular machine to regulate the supply pressure from 120, 110, 115 to, let's say, 80 or 90 that's needed by the equipment. Then how to address this gap between the set point and the actual demand requirement will present opportunity to further increase the efficiency and reduce the energy needed. So this leads to this other ARC assessment recommendation 2.4231. This is the code it's assigned to, but the recommendation itself is to reduce the pressure of the compressed air to the minimum required. And there's another one related to air compressor. It's to eliminate leaks in compressed air lines and valves, which are very common in manufacturing facilities. The former is recommended 122 times, okay, significantly larger than before, right? This is over 20%. And the leaks are seen in almost half of the assessments seen in 2023. Now, none of these talk about data yet, but in terms of pressure, since the leaks and the pressure set point all have something to do with the pressure of the compressed air line, what I want to do here is an illustration to see how we measure them and how we utilize the data collected. So we use two main types of hardware or instruments. One is a pressure probe that looks like this, where you can plug this into a spare port of your compressed air line. Usually there are tons of that on the factory floor lying around. And this can be connected to your cell phone app through Bluetooth, that you can read data in real time. It's also possible to export the data into an Excel spreadsheet and CSV file for further processing. We usually use this for short-term measurement. When we're on site, we deploy this and measure the data for 20-30 minutes. These two are pressure data loggers that are connected also similarly through, for instance, a quick connect to a spare port of compressed air line. That we usually leave these in the facility for a week or two to collect a relatively long-term data to understand how the pressure of the line changes from day to day. So the first set of data points that I'm going to present is obtained by this pressure probe. The time axis is in minutes and seconds. So this is the 14th minute of an hour. This is up to the 20th minutes of an hour. And this is 20th minutes of an hour to 32nd minutes of an hour. Okay. So here we see the change of the pressure of the compressed air line going up and down. This represents the discharge and charge processes of the compressor. And we can, from here, see the operating cycle. And these data are collected when the machines when they are operating. You can even see with a certain set point on your air compressor what is the minimum dip of the pressure before the compressor start operating and pick up the pressure again. And from these two figures, right, if we identify the minimum dip point, read the actual pressure. One of these could be 111 psi. This one is close to 119. And from here, with the data, we can pose the question, right? Do we actually need 111 psi in the facility, in the manufacturing process? Do I need 119 psi in the manufacturing process? If the equipment or the process do not require a set pressure this high, then it's possible to reduce this, let's say, by 5 or 10 psi's from the set point, and this can lead to a certain amount of energy savings from the compressor side. And it's possible to redo this study after implementation to make sure and verify if, with the change, the dip point is still stay above or with a certain safety margin above the process requirement. This is another set of data obtained by the pressure probe. It looks quite different from the one we see from the previous slide. The horizontal axis is still, in terms of minutes and seconds, the 45th minute to the 5th minute mark of the next hour. If you look closely, right, the vertical axis presents a much smaller range compared to what we had before, right? This one is about 10 psi, and this one also about 10 psi of the range. But this new one is only about 2 psi's in total of the range. And if you look at the readings, the line pressure bounces between about 106.5 psi to 108.5 psi. And what we discover for this particular facility is they have a regulator installed immediately at the outlet of the compressor. And while the compressor was set with set point pressure of 120 psi, that regulator immediately reduces that to 110. In that particular area of the manufacturing floor have the compressor serving a number of CNC machines, which do not even require 90 or 80 to 90 psi's in the maximum. And by observing this, firstly, we can clearly see the pattern, the abnormal pattern from what we had before. And then by reading the actual numbers, we can identify issues that are potentially existing in the setup of or the configuration of the compressed air system. Now, the data can get much more complicated. We'll present a few more complicated, more involved scenarios, which is not very complex, but for users, especially with the goal being reducing energy use or improving energy efficiency, there's no need to apply very advanced engineering or mathematical statistical tools to analyze the data. The most important thing is to understand the patterns of the data. What is a normal pattern, like the one we have here? And what is the abnormal pattern, like the one we see here? As soon as you can tell the normal pattern from the abnormal pattern, then you can focus on the abnormal pattern and try to identify what is the issue with those. I have more examples in the next few slides. Now, these are shorter term, right? We observed this for 15, 20, 30 minutes. Now, these pressure loggers we deploy also by connect this port with the spare compressed air port in the facility. And we can look at it in the larger time scale, let's say multiple days. And this is the line pressure reading for one facility during one day last year in December. And by looking at this, right, what we can observe is there's no line pressure before certain time in a day and after a certain time point of a day. And in between, when we look at it, we can first identify the minimum, the dip point, about 112 psi, right? So that's still the question we can ask. Does the process need 112 psi? If it doesn't, can we reduce it, or how much we can be reduced? And also when we look at the patterns, right? This is, as I mentioned, this is important. We can possibly see two different type of patterns. The first type of pattern is this clean or cleaner up and down pattern. Right? Go up and down, and every time it goes up and down, how much it goes up and down are similar. And this appeared both at the beginning of this time frame and at the last of the time frame. These are the periods, from our interpretation, are when the compressors are idle. There are no demand downstream. So the compressors go up and down, and the up and down are because of the leaks in the facility that are drawing compressed air and letting the pressure drop. But the compressed air compressor will keep up the set point. In the different levels we see here, maybe due to the sampling interval or sampling frequency that didn't catch the maximum along the way. But other than that, we see the cleaner up and down pattern at the beginning and then last. Now, the middle point, apparently the pattern becomes a little more messy. And this is what our interpretation is. This is during the active production period, where the demand downstream can vary, and the intermittent nature of the demand can cause the operation or the line pressure reading become up and down, more unpredictable pattern. But from this, what we can directly see is these two idle periods represent about 6 hours of time during a day when no actual production is taking place. So does the compressor need to be running during this time period? If not, then this represents, as I mentioned, 5 to 6 hours of reduction of the operation time. And if this compressor operates with relatively high power, then this can lead to a lot of power energy savings and eventually cost reduction. And from this graph as well, if the company is worried about whether or not we can start the compressor in time for the actual production to start, this graph also shows and can be seeing how fast the charge time will be. And this can be used as a guideline to plan the startup of the compressor or other equipment that have similar natures that are supporting the certain process, but has a certain warm-up time. Now, for our compressors, we can measure the line pressure easily. That's usually relatively non-intrusive, because if you have a spare port on the compressed air line, you can connect the sensor and get the reading. There is a more intrusive method, and this particular approach applied not only to air compressors but to other electricity-powered equipment as well. That's the current transducer, which is like a clamp meter that can go over one of the phase of a three-phase equipment, or if a single-phase equipment is one phase, can read the current data, current draw of the equipment, and eventually, if we know the voltage, we can approximate or estimate the power draw of the equipment during a certain period of time. So this is another set of data we obtained by, in this case, the current transducer. The horizontal axis will still be the time, so from midnight up to the next day. This is the 24-hour of data. This is the current reading, so this is in amps from 0 to 300. Apparently, this is a very high power equipment that we're measuring here. Can take current up to 300 amps. And again, as I mentioned, right, for engineering studies, of course, you can apply various fancy tools or methods to the data, but in many cases, you don't even have to go into that. We want to focus on the patterns. So let's look at the patterns, right? We'll have, again, this beginning portion of the pattern that'll go up. There's some ripples and eventually go down and up again. It repeats itself almost periodically for a certain period of time. And there's the latter part, right, where you don't see the dip of the current to 100 amps. It remains within, just 250 to 300 range, where with rare drops could be due to certain reasons. And then we have the middle part, right? This kind of mix of the two. You have this up and down with the ripples, but also there's certain period of time where the current draw is significant with no drop in between. And interpretation, this is an air compressor. Our interpretation, again, the first part is the compressor is idle, doesn't have any job to work on. The up and down, the load and unload cycle is because of the leaks in the facility. Then during this period of time, the demand from downstream is high, so the compressor have very few chances to go down to a resting mode or energy efficiency mode or sleeping mode. And during the intermediate use part, there are some period of time where the compressor can go into sleep mode, but there are also periods where the compressor have to work hard to keep up with the demand. But again, my point is, while looking at the data, look at the either daily, hourly, or monthly, but try to focus on the pattern. And in this particular case, we have identified this idle period, and we can see on average is drawing 200 amps when it's idle. We can further do a quick math, right? We have 200 amps of electricity. Let's assume it, in this particular case, it's from midnight to 6 o'clock or even 7 o'clock in the morning. Let's say only 6 o'clock. This is during the weekend time. And let's assume this 6 hours will be repeated every week for 50 weeks. And again, assume 15 cents per kilowatt hours of the electricity cost. We can calculate if the equipment runs on 460 volts, 200 amps of average current as we see from the previous data. If it's a three-phase equipment, it consumes at about 160 kilowatt, which is a very high power. One is idle. And if this is for 6 hours per week and 50 weeks, this energy when it's idle is consuming close to 48,000 kilowatt hours of electricity, and the energy cost is over $7,000. And if this is true not only for 6 hours, but maybe let's say 10 hours or 12 hours, this number will get even larger. And if there are multiple equipment having the same operating schedule, the cost can add up very quickly. But all of these can be seen directly by the data we have through the sensors we deployed. So those are our compressors. As I mentioned, these can be done for other equipment, like this is for 2 injection molding machines. And again, we will see the current measured from the equipment going up and down for different peaks and valleys. But as I mentioned, the major task to identify energy efficiency opportunities is not to go into these details, but understand the patterns. Now, for the graph on top, we can quickly see, well, there's no operation here. Well, there's a certain period of time that you have a flat reading of my current, and there are in this particular in the graph underneath, there is this period where the energy draw is very low, but it's compared to the other parts, but still significant. The current can still go up to 40, 50 amps or 30, 40 amps. And this can be dramatic when we add this together, and assuming this is not only for a day, which is shown in here. If this is multiple days in a week, in multiple weeks in a year, when we do the multiplication, this can add up really quick. Now, this 2 graphs are for 2 injection molding machines. And again, by identifying these opportunities, by identifying and quantifying how much current are being drawn from here, we can quickly understand how much energy can be saved by eliminating entirely this idle period, or at least part of this. Now, data-driven approach is not an easy thing to do, but it has a lot of power. It can help us verify and quantify opportunities and confirm, validate actions. Right, as I mentioned, right, we focus on the data such as pressure, temperature, current. Those are measured in real time by advanced tools and devices. But there are equipment nameplate specs, nominal operation schedule. Those are also data points available directly to the facility, to the customer, to the company that can be used directly to quantify, do some ballpark estimation of their energy use and identify opportunities. But there are also even more direct things like the rate schedule, charge rates, policy regulations, even the available programs, grants that the company can take advantage of. Those are all data that should be viewed as data from our perspective. Now, the ways to carry out this approach, to implement this, of course, first is you should know your options, and you can know your options and can shop around. Right? There are multiple ways to do certain things. There are different suppliers of natural gas, of electricity, of propane, of heating oil, for instance. Have you utilized all your options? Have you explore the flexibility and different options that you can utilize to fulfill certain objectives? And then understand your process equipment requirements, right? Those are directly available when you have your manufacturing process constructed, when you have the equipment brought to the floor. You know how much compressed air pressure will be needed, and then try to connect that with the personnel or with the team or with the vendor or contractor who will be setting up with your equipment, and try to monitor the performance of those systems on a continuous basis. And when you have the capability to obtain engineering data, understand the data patterns, and have the capability to identify anomalies, is much more important than understanding every single details of the readings from the data, as I just illustrated through the examples I show. The next step is easy to say than done: align, plan, and practice, right? This requires a lot of communication from various levels in your organization, training of the operator, and again, continuously monitor the performance and making continuous improvement to refine the process. This is an ongoing process for everyone from every organization, even from within ourselves. But this is the main step that everyone needs to take to make the actions into values. And finally, we always recommend and encourage our clients to be proactively seeking identifying resources they can turn into, right? They have utility providers, state agencies that have great programs, incentives. They have universities that have great programs like what ECU is offering, like all the IECs are offering. There are other programs offered by the DOE, by EPA, EDA, other federal agencies, and there are some third-party vendors and contractors that you can utilize to bring up the level of practice in the facilities in terms of energy efficiency, operations efficiency, and whatnot. And in terms of the resources that are very accessible to small, medium-sized manufacturers, we have our IEC, and we have from next year on-site energy technical assistance partnership program under the DOE. We have 10 different regions that will be covered by different some universities and also commercial companies covering different regions. And there's also programs such as the NIST MEP programs that can help manufacturers accomplish various things, from business models to technology scouting, that can bring great benefit to manufacturing organization communities across the nation. And we also have a lot of software tools developed over the years that the DOE programs are using, and many of these can be easily trained and used by engineering personnel in companies and manufacturing or commercial users. And the two final things I want to mention is the IAC implementation grant is part of the bipartisan infrastructure law. It's $400 million. It has two work streams. One is through the assessment by the IECs, work the combined heat and power partnerships. The second streams are for assessment done by other organizations that have to be recognized by the DOE as IAC equivalent. The first round was opened in June, concluding July 14th, very short period of time. And we have 41 manufacturers selected across the nation that will receive a combined of $5.2 million. So on average, each company selected will receive $10,000. And this grant is designed to help offset the capital cost for some of the energy efficiency measures that the small, medium-sized manufacturers want to implement through the assessments done by these organizations. New rounds of the implementation grant are being considered on a rolling basis now. They're reviewed quarterly, but the submission application can be submitted anytime. But as I mentioned, must have either an IEC assessment or DOE recognized IEC equivalency assessment. Now, what I have talked about in this talk are focused more on the industrial side, manufacturing facilities, for instance. The DOE has announced this Building Training Assessment Center program earlier this year. the proposals are in August, and they expect to make selection in the fall 2023. So I would expect in later this month or maybe in November there could be announcement. So for commercial users, this could be commercial buildings, for instance, and schools. This can be an opportunity similar to the EIC program that can bring benefit to the general communities again. So we're all aware of these two goals set by the administration: zero carbon electricity by 2035, and net zero emission economy wide by 2050. These are very ambitious goals, and the way to achieve that is to have everyone act from their own side and to utilize as much as assistance as possible, to share knowledge, share best practices, and one of our job is to bring these benefits, especially best practices, to the companies, to our clients, to enhance their operation. With that, that's the end of my presentation. I'll be happy to take any questions, if any.
Yeah, thank you so much. We have a couple questions in the chat. First question, would the PowerPoint be available to everyone after the presentation? So the recording will be available. So I don't know if Dr. Zhang would be willing to share the PowerPoint with us.
Yeah, I can share that. Yeah.
Okay, that's perfect. Second question, why not just have a large compressed air storage tank to store the energy for later use and the turn off the equipment for many hours?
The energy storage, the compressed air storage tank solution is usually used to maintain intermittent, kind of as a buffer. Usually, it's not used to sustain a extended period of time of use for many facilities. And when it comes to storage, there are also risks of leaking from the storage that cannot be later used effectively as it was planned. So many of the facilities we've been to, they do have storage tank, and many of those are very large size storage tanks. But as you have seen, when the compressor shuts off, there will be leaks in the system somewhere, and even for the air contained in the storage tank, they will slowly decay and leak through the lines to the ambient. So that's one of the reasons that this is not a common practice that we have seen.
Okay, thank you. Another question, Professor, in your experience, do companies tend to have greater cost saving opportunities in changing equipment runtime, fixing air leaks, or both?
It depends, but usually both eliminating leaks and reducing operating time usually will lead to larger returns, and usually it's quicker because it can easily be implemented. For eliminating leaks, that's a little tricky because it requires an additional leak detection program that will go into the facilities, look at all the valves, the governors, the regulators, and the filters to identify the locations. And then on top of that, have the personnel or the staff to repair those leaks. And depending also, again, the effectiveness of the repair, the leaks usually cannot be 100% restored. But reducing the operating hours, that's usually easily implemented by setting up the timer or schedule shut off of the equipment, and make sure they have dedicated personnel to shut off the equipment when they leave the manufacturing floor.
Okay, thank you. Any other questions? Okay, it seems we do not have any other question. Thank you so much. So our next webinar will be on November 9th, not
Okay.
October 9th. Yeah, so there is a mistake here. And it's Thursday, November 9th from 2 to 3. And the title of the webinar is Industrial Decarbonization Pathway for Innovative Change. Okay, thank you so much.
All right. Thanks, everyone.
Thank you.